My name is Olga.
And I'm Gijsbert.
We are, just to say now, we're software developers from ING. We are working on a generic streaming application platform for ING business users. And we, of course, use Apache Flink for it. We want to talk to you about the little challenge that we have encountered during our development and how it has been solved. On the agenda today, we are gonna, On the agenda today, we're gonna talk, of course, what ING is. It is a bank, spoiler, about what is the use case, what we are actually building, and then we will get technical with some examples and code to see. ING is a rather large international bank. Only in the Netherlands, we have almost 9 million customers. Those customers are also making 9 million transactions per month on the ING ATM machines. They have 1.45 million logins per day on the ING website. And the banking app is getting hit with 4.2 million logins per day. So that's just a little bit on the scale that we are working with. And let's talk about the use case. We need to develop a platform which should be and that platform, the business logic of it, should be possible to be modified without IT involvement. So the business users define some business logic, and they deliver it to the system, and it just works without our contribution to that. ING users, customers, systems, they all produce all kinds of events. For example, usage of the ATM machine is becoming an event on the ING Kafka bus. If someone is using a mobile application or a laptop to do some mobile banking, all this is becoming events on the Kafka bus, and we need to perform some magic on it to determine some kind of information about those transactions. The subdivision of a use case that we are focusing on today is fraud related. So we are detecting fraudulent transactions today. And every transaction is getting marked with a label, is it fraudulent or not? The point is, of course, to stop the fraudulent transaction from happening. So it has to happen pretty fast. We're not going to focus on what the magic is today. It is just some machine learning happening, defined by our business users. We are not even supposed to know what that is. However, if you have some machine learning, you typically need some extra input. Not only the input that you have in your original event straight away, but also some kind of characteristic that requires some more calculation and state to be kept. We call those features, and typical examples of these could be the speed that the client has moved from one point to another, if a debit card has been reported broken before, if a customer has been blocked because he is a fraudster. We need to know this state in our system, and we need to supply this also for the model to be scoring our model. The requirements of the use case, well, the most important one, and also what we focus on today, is it has to be dynamic. We need to be able to change the business logic application without restarting the Flink job. 2 reasons for it. Well, first, the business users have to be able to do it without us. And second one, we of course don't want to be stopping the fraud detection while we're updating the fraud detection rules. We need to be able to keep historical state, and the scale of real time has to have 100 millisecond response, and the volume is pretty high. We have like 10K transactions per second. Another important thing, it has to be scalable, because otherwise how can we make sure that we keep performing, that ING is growing, getting more customers? A little overview of the architecture. The system is a black box, Kafka in, Kafka out. The messages come in, getting scored by the magic, and then come out with a label. The definitions are coming in via separate Kafka stream. We have developed a DSL to define the business logic, and then the DSL is arriving. We parse it, and the system knows what it actually has to be done. The definitions also define how to prepare the information to input it into the magic box, and then that's also pretty important for us. A little disclaimer here. We are not allowed to share the actual business rules that ING is using to detect fraud, of course. We are also not allowed to share the internals of the ING systems, just the basic overview. And for our purpose today, we have come up with a pretty typical example of a model that you could use for a fraud detection. You can find it on the internet anywhere. We have also modified it to our liking to suit the presentation a bit better, but be aware, this is not the way that ING is detecting fraud now. And we give it to Gijsbert so that he can explain what's going on.
Thank you. So I'm going to talk you through the basic use case that we're going to use as an example throughout this presentation. So this is a very standard use case about how fraud could be detected, and this use case is called the flying carpet rule. So the flying carpet rule is the following. If you want to travel from Amsterdam to New York, you have to take an airplane, and it takes you a little under 8 hours. So suppose that some customer does an ATM withdrawal at 1 p.m. in Amsterdam, and then half an hour later he does an ATM withdrawal in New York. Then you know something is going wrong here, because he can never physically reach New York in just half an hour. So we are going to try and detect this pattern. So in order to detect this pattern, we're going to need to keep some state in order to determine the customer speed. So the transaction you see here could be the transaction event that the ATM machines will generate for each withdrawal. So in order to compute the speed, you can use the location and the event time part of this transaction event. So if you keep for one particular customer the state of the previous ATM withdrawal, particularly the location and the event time, then when a new ATM withdrawal comes in, you can use this information and calculate the customer speed. So how would this Flink job look like? Well, the basic Flink execution plan is as follows. We have the incoming Kafka events, and these transaction events are first keyed by customer ID, because we need to keep some state per customer. So after it is keyed by customer ID, it is sent to the next rich stateful operator, which will get its state from the previous ATM withdrawal, determine the speed, and then update the previous state. So then the customer speed is calculated, added to the original event, and sent to the next operator, which will score the model. And yeah, in this case, suppose Olga does a PIN transaction. So the event comes in either node, we don't really care which node, and after it's keyed by customer ID, it will end up at one particular node, which is responsible for keeping Olga's state. So from the state, it can see that Olga did the PIN transaction at 8:30 in Alkmaar. So Alkmaar is also a Dutch city, and as you know, the Netherlands is a pretty small country, so yeah, it is possible for her to reach that. She was just traveling at 32 kilometers per hour. So this information is sent to the next operator, and there the model is scored, and we get an OK back. So if, for example, Jens does a PIN transaction in New York at 11 o'clock, then if you key by customer ID, which is Jens, it will end up at a probably different node. And if this node then has the previous state that half an hour ago he was doing a PIN transaction in Amsterdam, then apparently he was moving extremely fast. So the model will say that Jens is a bad boy and he's not allowed to do this ATM withdrawal. So now Olga is going to show you some code, how this job is going to look like.
Let's put on my mouse. Okay, here is our typical simple example. We have set up the environment in some way. We have a parallelism more than one, otherwise what's the point? And we have an input stream, At this point, it is just a random generated input stream to simulate some Kafka events of a type simple transaction, which has the same information as Gijsbert has described. Now, to get the customer speed, we have to key the input stream by the customer ID. And then we're using the map with state operator to keep the state and calculate the speed. We could also use here any other rich map operation that we could use within Flink API. But for this presentation, we chosen for map with state because it's quite compact. What we need to receive from it is enriched simple transaction, so not only the transaction, but the speed. And we are keeping the customer state, which is previous location and the previous time of the transaction. Well, what's going on inside? Well, we are calculating with speed, with our beautiful business logic, which we don't care at this point. We are producing the enriched transaction event by copying the transaction, adding a speed to it. We also are preparing the new state that we are going to store at the, for the future transaction to calculate the speed then. And then, as a map state works, we need to return a tuple of enriched of a produced event, enriched transaction at this point, and optional new state that we're gonna have to keep. Now we have this enriched customer stream with a speed, and then we just simply map it, and then we score the beautiful flying carpet model with it. By the way, the code is on GitHub, so you can check it out and see for yourself how it works later. And for now, that's all on the code part. Gijsbert will continue.
Okay, so as you might have noticed, the model that we were scoring here. Oh,
no, sorry.
Yeah. The model that we are scoring here is quite simplistic, so it's not really unlike any of the real models that are used to get to indicate fraudulent transactions. So let's improve a bit on this model. For example, we could not only look at the customer speed, but also at the average amount that has been withdrawn for this particular card. So if somebody always just withdraws 10 euros and then immediately withdraws 10,000 euros, that might be an indication that something is wrong. So in order to determine that part, we're going to have to keep two different pieces of state. We still have the customer state as before, and we also can keep up the card state, which is the total amount, so the sum of all the amounts of the withdrawals in the past, and the total number of transactions. Divide one by the other, and you get the average amount for this particular card. So if we want to determine these two features, then there are several different approaches. The first approach would be the sequential approach. So just as before, the incoming events are keyed by customer ID, the customer speed feature is determined, and after that, the event can be keyed by card ID and sent to the next stateful operator, which will update its state and also calculate the average amount for this card. So if, for example, Olga does a PIN transaction, then as before, first it lands on node A, where the speed is calculated, and after that it's obtaining a different key, so then it's at node B, and there the average transaction amount is determined. And then the model is scored again. And the same thing happens for Jens, who is still not allowed to do his ATM withdrawal. So let's look at how this job would look like.
Okay. Sequential job. Okay, we still have the same environment and the same input stream. We are keying it by our customer ID, and there inside we're calculating the speed, exactly the same way as we have done before. Now, having this enriched stream with speed, we also we get it and we key it again by card ID. There we calculate the card state, pretty similar, we calculate the card average amount, pretty similar way as before, beautiful business logic, different one at this point. And then we are producing, again, a transaction enriched, not only with speed, which has been done before, but also with the average amount. This fully enriched stream with all the information that we need to do our improved scoring model scoring. We send into a map and score again. And that's basically it. Not very different from the previous job, just one more step and one more key.
Yeah, so let's evaluate this method. The only real positive thing is that it actually works. The pretty big drawback from this method is the fact that if you have a model with, say, 20 different features, then the event has to go through 20 different operators sequentially. So it does not scale very well, and also the latency will increase enormously. Also, a drawback of this method is the fact that if you have several different models, different events scoring these models, then events that will go through all the nodes, but for some events might be used for just 1 or 2 models, and they will not need all the state. So yeah, it could be solved with a filter, but still, it is slightly annoying. Also, as Olga said at the start of this presentation, we had to dynamically add new keys, and right now the execution plan is fixed. So if they want new features, then we need to do a redeployment. So let's at least solve this latency issue right now. So another approach could be the parallel approach, where the incoming stream is first given a unique identifier, which is used at the end for aggregating the information, and then the stream is split up in 2. So the first part of the stream is keyed by customer ID, just as before, and the second part is keyed by card ID, and the next 2 stateful operators will then handle the events in parallel. And after that, the outcoming streams are again keyed by the unique identifier and sent to the next operator. And this next operator will do nothing except just aggregate the information from the 2 streams again. So yeah, this is how it will look like if Olga does a pin transaction. Yeah, so let's look at how this job would look like.
Okay. Parallel job. Ding, ding. Here it is. Well, we have still the same input stream, and then we need to assign a unique identifier to it. Well, we didn't go very deep here and just use the random Java unique identifier. Not very hard. We also have prepared already the type of the event just for our convenience, and it's an enriched transaction, and it has to have customer speed and the customer and the transaction amount of a card. Well, let's actually key the stream. We key it first by customer ID. We calculate the speed, same way as before. Not going to zoom into it again. And then the same stream, so it is kind of split. We are keying again by card ID, so that it can in parallel calculate the average card amount. We do that also the same way as we did before. Fine. Have these 2 enriched streams, but one of them has the speed, another one of them has the average amount. We need to get them together so that we can actually score the model. So we need to get a fully enriched stream. To do that, we are keying both of the streams by unique identifier. We are connecting them with a connect operator, and then we send it into a flat map where we actually do the joining of the 2 events into 1. Well, how do we do that? It is the reach call flat map function because it has 2 inputs. All the types are the same, just for us to be handy. And that join function is going to have to keep 2 types of state, customer speed and the average amount. In the actually flat map method, what we do is if event arrives and we have already received the previous event with, for example, the average amount, because the order could be quite random there. If we have received already at this point the average card amount and the event that we have received contains the speed, we can connect them together, produce a fully enriched transaction, and collect it. It is pretty important to not forget to clear the state at the end, because otherwise we are just leaking memory. It's a bit stupid. If we didn't receive all the events that we need yet, and it's only 2 at this point, we just put the customer speed in the state to keep it for the next, for the time when the other event is arriving, and then we can produce the fully enriched transaction. Yeah, well, the other flat map looks pretty much the same, only then you go from the point where the other event has arrived first. We have joined these two streams now. We get the fully enriched stream, then we score it in the map the same way as we have done before.
Okay, so let's also evaluate this approach. So one of the advantages is that it's better scalable and the latency will be better than the sequential approach that we talked about earlier. Still, we have the drawback that events have to pass every node, even if the state is not required. And also, we can still not add new keys dynamically, because still the execution plan is fixed. Another drawback right now is the fact that the execution plan is more complicated, especially when you have, say, 20 different features that you need to calculate, because you can only join 2 streams at the same time. So if you want to join 20 streams, that's going to be hard. So now let's go to our final example, where we finally will use the dynamic key management. So remember this slide that Olga showed at the beginning? The definitions that were stored here will actually store 3 separate pieces of information. It will store the actual models that need to be calculated. It will store information about how to compute the features that are used for scoring these models. And it will give you information about how the keys are defined. So the advanced approach will look as follows. First, again, a unique identifier is added to the event. This unique identifier is again used at the end for aggregating all the information. And after the unique identifier is added, then the event will be sent to the next flat map. This next flat map will actually contain parts of the definitions, and it will, from the definitions, then read and get information about how to copy the how to create a number of artificial keys. So remember that before we did a key by customer ID, which is only the value of the field customer ID. And right now, an artificial key will look like this. So not key by only Jens, but customer ID equals Jens. Now, why do we do that? In the next operator, it will receive a KeyedStream and it will need to know which feature this is going to determine. So it can use the first part of this artificial key to identify the feature. So the first part is of this stateful operator is it will generate a number of artificial keys. And after that, for each artificial key, it will create a copy of the incoming event. And it will send out all these copies. So if you have 20 artificial keys, then 20 different events will come out of this operator, which are all keyed by this artificial key and sent to the next operator. So this next operator, it has the purpose of it's going to determine the feature for us. So this operator also needs part of the definition, mainly the part where it knows for this feature how it's going to use its state to determine the feature, and also how it needs to update its state. So again, here, this operator has created 2 separate events, which is sent to the next operator. Here, the next operator will look at customer ID, and then from that part, customer ID equals, it knows which feature to determine, and it will use the same business logic as before in order to determine the customer speed. Then at the end, these things will be sent to the next operator. And here I have to admit that I kind of lied to you guys with the best of intentions, because I said that this operator will create a copy of the event for each artificial key. But in fact, you do not want to do that because you want to minimize the load on your system, especially when there are a lot of transactions coming in. So this operator will not create a copy of the event. It will only copy the information that is actually needed by the next operator to determine the feature. So for customer speed, only the location and the event time will be added to the artificial key and sent to that operator. But in the end, you need your original event again. So that's why, from the start, the operator that added the unique identifier is also sending its information to the next operator. So here we finally key by the unique identifier, and we send it to the next operator, which will then aggregate the information. So similar as before, it just stores pieces of incoming, so incoming features in the original event in state until everything has come in, and then it will add it will aggregate the information and forward it to the next operator, which will score the model again. So let's look at this job.
Okay. Let us zoom in slowly on it. Well, we have a uniquely identified stream. We here, for our convenience, just to make it simpler, we not only generating the random unique identifier and adding it to the transaction. We also here have the knowledge of how many features we have and how many keys we have defined to know the expected amount of features that we need to get at the end. It is just for us to make it handy. It's also a good idea to not copy the statically typed event anymore here, but convert it into a map and put it in a transaction. Yeah, a little disclaimer here. We are using here a manager object, which has at this point hard-coded definitions, just a list of keys that we have defined for now for our presentation. In the real world, it's not a good idea, first of all, to keep it all in a singleton. Second, you of course want to have it dynamic and get it in via a separate Kafka stream. To do that, you will have to use keyed broadcast state of Flink, which has just been introduced in 1.6, as far as I know. And I also know that it has been discussed in the advanced session on how to actually do that. So that's all the information I'm going to give on that for now in this presentation, because otherwise it just gets too long. Okay, we have produced the uniquely identified stream, and we have also their knowledge of the amount of keys that we need to get. And now we have to copy the event the same amount of times as we have keys. We do that here in the flat map operation, which is going to produce an artificial key event for us. Well, here we also have a manager which knows the amount of keys that we need to, and what are those keys that we need to calculate the features for. We're calculating the key value by just getting the value of the key from the payload, and it's basically just a key object of field and a value. We are calculating the, we're also adding here for our handliness the name of the feature, just to know later what is the feature that we need to calculate from this event. And we are filtering the required payload to not copy the whole event over and over again, because that's inefficient. We can produce an artificial key event here and collect it, and then it's getting collect as many times as we have keys, because we have a for each here. Artificial key event has the unique identifier, the name of the feature, the value of the key that we're going to use to be keying with, and then the other information that we need. So now we have these events, but we need to actually get the data for those events. And we do that by keying them by artificial key, so that we are sure that the that the feature is being calculated at the node where we are actually having the data, because otherwise it's incorrect. And then we are using the map with state to calculate the features. Well, here we also have to know how to calculate the features, so the manager object is involved again. Here inside we have encoded our business logic, which we have same as before, same logic. And it also knows not only how to calculate the result of the feature, but also what is the state that it has to be keeping for the next iteration, next event that has to be calculated. Having these results, we produce a feature event, which needs to contain the unique identifier to actually know how to connect it with the other features and the original event. The feature name, to know what is actually going on there, the result, and the expected number of keys for us to know when we are ready, collecting everything. So, and of course, we have to keep the new state that we need to keep for calculating the future features in the future. So we have a stream of features, and we have also the stream of original events uniquely identified by unique identifier. We have to connect them. We do it pretty much similar way as we have done before. We key it by unique identifier, both of the streams. We are connecting them, and we are using a flat map to join the streams. The joining is also a rich flat map function, pretty much the same as we have used before. The only big difference here is there is one original event still, but there is multiple feature events arriving there. So the state is not a value state anymore, but a map state. So here we keep the list until we have received everything that we need for us to produce the fully enriched event. We know that by comparing the number of the feature events and the amount of expected keys and expected features. If we have received everything that we need, we produce the event, and then we collect it, and then we are done. So again, this enriched stream getting into the map and being scored. That's it from the code point of view.
Okay, awesome. So let's also evaluate this final approach. So the big advantage of this approach is that we finally became dynamic. Because if people want to improve on the model, need new features, they just have to write a new DSL or extend existing DSL, stream it in, and automatically the job will pick it up and change its business logic. Also, the DSL right now defines which nodes events are going through. So if an event does not need to pass through a certain node, it will not do that. Another advantage is that this execution plan looks a bit simpler than the parallel approach that we had before. Well, it's not completely true if you actually use side inputs. So if you do a broadcast stream with the DSL, but still it is very maintainable execution plan. So one drawback is that inside of the operators, the business logic will be a bit more involved. So yeah, it's a bit harder to understand what's actually going on right there. And also a drawback is that we need to provide other people a way of describing the business logic. And even though it's a fun job, it's a lot of work. So yeah. So now, for the conclusion, we have concluded that even though the Flink execution plan is fixed, your business logic does not have to be. So with just a little bit of out-of-the-box thinking, you can get a lot done with Flink. So that was our presentation. You can check out the code on GitHub here. Are there any questions?
First, thank you very much, Olga and Gijsbert, for your talk today. So thank you. And yeah, we do have a few minutes here for questions, so I'll open the floor here.
Yeah, thanks for the talk. You mentioned the broadcast stream, where you probably also add additional features at a later time. You didn't cover a strategy how to backfill, aggregations that these additional features would cover. Do you do that, or
what do you mean by backfill?
Now, if you have like windows, and then you need a couple of windows to like.
Yeah, well, in our production code, really, we are not using windows because it was just not possible to implement this with a Flink window operator. We are using process functions with timers to simulate the windows. So.
Great talk, thanks. Last year I saw a presentation from ING and they were explaining that for the scoring they use PMML and open scoring. Yeah. I'm struggling personally with my data scientists because they are fighting against PMML. Do you have any view on that?
Well, we are the same people from the same team, so we are using PMML. And I don't think there is any other way for us at this point to do it differently. So yeah, the only thing that we can say is let's just improve the open scoring IO library and the PMML format if we need to.
So if you add a new feature, then you most probably also need to add new code that can compute this feature. How would this work in this framework?
Well, we have a pretty complex DSL and a pretty complex code which is converting this DSL into expressions, and then those get executed. So basically, if you add a new feature, you add a new object of a feature. So you convert the DSL into a feature object which knows how to calculate itself with an expression and that kind of stuff. But it's a pretty complex code. So that.
Okay.
Yeah.
So you only use the Flink for model serving and not training yet, or is it a plan to do online machine learning with Flink?
Well, it is a plan as far as I know, but far ahead in the future.
Thanks.
We've got time for a few questions. So.
How do you embed the model inside the DSL? Is it just plain text?
Yeah, it's a plain text in a PMML format, portable model something language. And then, sorry. And then that one is basically an XML string which defines the model, and then that is just easy to stream in as a text. And then that one is being parsed by the OpenIO library, and then that one can do the scoring.
Yeah, so actually what comes in from Kafka is just a string containing the PMML, and what is stored in the definitions is a case class which can be evaluated.
Why is the model streamed over Kafka? Is it a model that changes often then?
Yes.
Or? Okay.
It's also a model, yeah, it changes often, but we're also adding new models constantly. So, yeah, that's why.
Anyone else? Yep.
Just a question on the last implementation you've shown. The fact that you connect at the end with the initial events, does it make any overhead in terms of memory? Because you have to wait that all the previous steps finish before going to the next steps, and then you need to hold all the incoming event in memory?
Well, of course it's overhead, but hopefully this happens pretty fast, because yeah, how long does it take to calculate one simple feature in parallel? So this has not become a problem for us yet. Yeah.
We have time for one more question.
Anyone?
Bit of a follow-up question. Have you considered sending all the fields with the first artificial key instead of reconnecting back with the original event? Have you evaluated the performance of both?
Yeah, we have, but we are using the setup with a lot of nodes, preferably on different machines, but then the network gets more full, and we really want to avoid that. But yeah, if your network is fine with just copying everything all the time, make it simple for yourself, just copy it.
Sorry, I don't mean copying all the time. I mean just with the first artificial key, and then the other artificial keys, you should just send the values that you need to do the computation, but then you avoid the join back with the original UUID stream.
Yeah, okay, that can be done, but...
That could be also a valid option. Yeah. So there are a lot of different ways to reach the end goal, and we have chosen for this one. This one works pretty good for us, but what you said could also be a very valid option, I think.
Okay, thanks.
All right, I think that's all we have time for now. Thank you again, Olga and Gijsbert.